All right, so now let's discuss friction. Here's a question that we're going to kind of use to frame our discussion of friction here in the beginning. So if you want from your readings or from what you may already know, go ahead and give this a try and see what you can come up with, and we'll talk about it. Okay, so when I do this problem, I got an answer of B, 2.45. So let's just go through then and talk about friction as we go through and look at this problem. So the causes of friction, all surfaces are very rough on a microscopic scale. So here we have this person standing on a floor with their shoe. There's friction there. And so what's actually happening, they show a blow up. So when the two surfaces are pressed together, the high points on each side come into contact and form molecular bonds, which is kind of what they're drawing over on this side here. So these are like the molecular bonds, which we can think of our molecular bonds as sort of little springs in between the atoms. And the amount of contact between these bonds depends on the normal force. It depends on how hard the two surfaces are pressing. And so we're going to find out that there's two kinds of friction. There's static friction, which is when the two objects aren't moving relative to each other. So these bonds form pretty strong. And then there's kinetic friction, which is when they're sliding. And so the bonds don't form fully, but they do tend to slow the motion that's occurring. So as to start with, we'll talk about this idea of static friction. Again, this is when these bonds are really tight. And basically, so the figure shows a rope pulling on a box due to static friction, and it's not moving. And so basically, static friction, there's some maximum amount that it can, of force it can apply. And so if you pull on it less than that force, it won't move. So kind of like if you have, say, a heavy table in your house, you can usually push on it a little bit, and it won't start moving until you push strong enough to actually kind of, break those bonds and sort of turn it from static into kinetic friction. And so in this particular example here of this rope pulling on the block, they've set up the forces. There's the force of gravity, the normal force, which this book calls little n. There's this tension pulling, and then there's the static friction going backwards. And so in this example here, there is no acceleration, there is no movement, and so what's happening is the tension exactly equals the static friction. And here the static friction is pointing opposite the way the object would move as if there was no static friction. So static friction has a maximum possible size, and as long as you push or pull less than that size, right, the object remains at rest. And so right here we can kind of summarize that with this equation right here. If the force that you're causing, if you pull on that object, it'll pull back with some force F of S. And as long as that's less than the maximum, it'll be able to do that. When you finally reach that point where you sort of reach its maximum amount, then these things will start to slide. And again, go back to that big table in your house. If you press on it, generally maybe you can press a little bit and it doesn't move, and it's only when you really give it a lot of force, when you overcome that F static maximum, that it'll start to move. And so it's not possible for the static friction to ever exceed its maximum, and its maximum is this equation here, over here. So mu s times n, again, I generally refer to the normal force as F sub n, but it's just the same sort of idea. And this proportionality constant, mu sub s, is called the coefficient of static friction. We'll talk a little bit about that more later. But let's look at the problem that we were looking at. So the problem that we were looking at, we were told that you had a box. So here's a picture of our box. So we're pulling on this block with a horizontal force. So maybe I'm just applying a tension perhaps. And so if we do our free body diagram, what's going to happen is we're going to have the static frictional force going backwards. As usual, we'll have our normal force going up and our mg. So I've sort of done the first couple of steps for our system. So I figured out the forces that are acting, and I drew my free body diagram. Now in this problem, you say that you pull with a force that's just large enough to overcome the static friction. And so what that means is we want to find our tension, okay, what we're saying is basically the tension is equal to what we call the force static, the maximum value, which of course what we just talked about is that it's mu sub s times the normal force. Now, typically, you'll be able to solve for the normal force in your problem, and here we can do that. So again, just to be careful, the equation I got from doing my Newton's second law in the x direction. So what I can also do is do my Newton's second law in the y direction. And in this case, we know that the acceleration is 0, right? So at this point, nothing's accelerating in any direction. Like we're pulling on this tension just to the point before it slips, and so it hasn't started slipping. And so that's the point where the tension exactly equals the maximum static friction. And so here in the y direction, my forces are force normal minus mg, sort of typical. And then because there's no acceleration up and down, my force normal is mg. This will happen often. You got to be careful. It won't happen all the time, but it will happen often. And so over here then, this maximum force that we're pushing with, pulling with, the tension is mu sub s mg. And so we're just at that point where the static friction is about to change. And again, physically, these bonds that we're forming, we're getting to the point where we're breaking those bonds, and we're going to start sliding, and so we move into the territory of the kinetic friction. And so let's look at that a little bit. Here's a nice picture that kind of describes this problem sort of in detail. So here's a graph. This is a graph of your the force you need to push or pull versus the different kinds of frictional forces. So here's the frictional force, and here's your push or pull force. And so basically we start at 0, and again what there is the force static maximum. That's the maximum force you can pull, and this where the static friction will sort of keep pushing against you. Again, it comes from those molecular bonds, and there's basically a total amount of newtons that you can push or pull with, where it'll just sort of push back. And so what's weird and kind of tricky about static friction is that if you look here at this point, okay, and so basically you start pulling. So you can think about this as just the same problem we were just looking at. I'm pulling with some tension here, and so suppose I start my tension at 0. My tension that I can pull will increase until it reaches this magic point where I hit that maximum static friction. And then what happens is those bonds break, and so now the frictional force as I slide it is less, and so you get this weird effect where all of a sudden the force drops down to the kinetic friction. And so kinetic friction has a very similar equation. I'll write it sort of in the way that I will typically write it, which is force subnormal here. And it's almost always true that the static force, the static coefficient, is bigger than the kinetic, again because of those molecular bonds. And then what happens is as I pull from then on, the frictional force stays the same. It has a nice constant force, which is why it's nice for us to talk about it right now, right? Because we're really good at dealing with constant forces. And so in our problem right now, that's what's happening. In our problem, we're sort of assumed that you pulled on this block until you overcame the static friction, and then you're moving with kinetic friction, and we want to know what is the acceleration after that. And so again, just to kind of reiterate, the kinetic friction force, just like before, is proportional to the magnitude of the normal force and this mu sub k, which we call the coefficient of kinetic friction. And again, for any particular pair of surfaces, we expect the static friction to be bigger than the kinetic friction. And so if we go back to this exercise we had, and so now I'm just going to jump ahead and say, okay, so I have this tension force pulling here, but of course in the problem we say that the tension force is equal to this thing here, mu sub s mg, right? Because it says you will pull with a force just large enough to overcome static friction, and that's that force right there. So now the force going against this is the kinetic friction. The same sort of forces here, Fn and mg. So I'll skip ahead. If I do my Fy equals may, of course that equals 0. There's no acceleration up or down, and so from that I can again get that the normal force equals mg. And so my last step here would be to look at the f of x direction. So my sum of my forces in the x direction, and so I look here. Now technically I would say T minus the force of kinetic friction equals m times a, the acceleration I'm looking for. And since there's only one acceleration, I'll drop the x part. But we have a little bit more information there. So for the tension, we're told that that's exactly equal mu s mg. And then for the kinetic friction, we know that that equals mu k times my normal force. Well, just like before, the normal force is just that mg. And so I can plug it in there and equal it to ma. And so here's the kind of problem where, if you notice, they didn't give you the mass because they know you didn't need it. So the mass will cancel in all these parts. And so if I solve finally for the acceleration, I get mu sg minus mu kg. And of course, if you really want to be slick, you can do something like this. You can say mu s minus mu kg. And of course, the mu's are given to us. So the mu static is 0.6. The mu kinetic is 0.35. And of course, we know g. And when I went through and did this, I got the answer of 2.5 meters per second squared. So that's a sort of typical maybe beginner problem dealing with friction. Just a few quick comments about the frictional force. So again, it depends on these two things, a mu and a normal force. Mu depends on the two surfaces involved, and so it'll depend on, if you've got two really rough surfaces or two really smooth surfaces. Has a maximum of 1 and is again smaller when there's less friction. So essentially, if you have a frictionless surface, what that means is you have a really small mu. The normal force depends on how hard the two surfaces are pushing together, which again determines sort of how many points of contact you have, and so how, between those molecular bonds, and so sort of how difficult it is to break that. And one thing that's counterintuitive is for us, okay, dealing with these sort of solid, non-deformable objects, the force of friction does not depend on the surface area of the objects in contact. And so what I wanted to do is just one more example here before we go. This is again a kind of a classic friction example. I think once you get to do these, you'll see this maybe as a not too bad of one. So on a rainy evening, a truck is driving along a straight level road at 25 meters per second. The driver panics when a deer runs onto the road and locks the wheels while braking. If the coefficient of friction for the wheel-road interface is 0.68, how far does the truck slide before it stops? So go ahead and give this a go, pause and try this, and then we'll go through and do our solution right now. All right, so the answer I get is B, and so let's go through and do this. So again, our steps here is, so I'll draw a picture of my truck. I'll draw a really sort of boring truck. So here's my truck. Maybe some wheels would be nice. Okay, and so what are the forces here? So basically we're going to, as usual, neglect air resistance, all that sort of thing. The driver slams on and locks the wheels, so that's a kinetic friction. And so what there'll be a force of kinetic friction backwards. And that should be the only force in the x direction. As normal, as usual, there'll be a normal force up and an mg down. And of course, it goes without saying, we'll just use our typical xy axes. And just like we've done a lot, this is one warning, is that, this happens an awful lot, but then there'll be cases where it doesn't, so you got to be real careful. This is a really common mistake people can make when they're starting out, is to always assume that the normal force equals mg. It doesn't always do that, but in this case it does. If I look at my forces in the y, I've got the normal force minus mg equals 0, which just leads me to the fact that the normal force equals mg. And then, and this is a kind of a weird case, you only have one force in the x direction. So the sum of the forces equals max. Again, what I'll do is I'll just drop the x since it's our only real acceleration going on here. And so it's the force of kinetic friction equals ma. And so now what we do is we unpack this to our new equation, mu k times force normal equals ma, and one last step, which is mu k mg. So again, I use this to plug in for that. And of course, what happens here is, like before, this will be real common because it'll be real often to have this normal force, right, having a mass in it. The masses cancel. And so my acceleration equals mu kinetic times g. Now I should be careful here. according to my coordinate system, this should be a negative acceleration. Hopefully it's clear from the picture, but yeah, the way I defined it, that should be negative. So it's negative, and when I did my mu k, which again they give you here in the problem, 0.68, I got an acceleration of negative 6.67 meters per second squared. And so now this is the final part of our steps here, is that sometimes they want you to find some information. And here they wanted to know how far does the truck slide before it stops. And so I think what I would do is this equation here. So this guy, and I know that my initial velocity is 25 meters per second. My acceleration that we got is negative 6.67 meters per second squared. And of course what I want to do is I want to find when velocity final is 0. And so I take this here, I make that 0 like so. So plus 2a delta x. And what I'll go through is solve for my delta x. And delta x, if I do this right, will come out to be v0 over 2a. And so if I plug in my numbers, I get 25, let's see, actually I dropped a negative sign, I think, because if I bring this over, there should be a negative sign. So negative 25 meters per second divided by 2 times negative 6.67 meters per second squared. What's nice is these two negatives cancel, and when I did this, I got an answer of 46.8 meters, which again, in our answer, we just rounded that up to 47. Okay, so a little bit of information on friction and some examples there. I'm also uploading another example video that has a incline with friction and an incline without friction to kind of get used to that sort of thing. All right, thanks a lot. We'll see you in class.